Our primary task in introducing the concept of projectors and positive semiconductor matrices was to talk about measurements. Measurements were necessary to obtain output from the system. We know what the state of the system is, we know how to operate on them using unitary operators, but then how do we get the output? It turns out in quantum, measurement operators are very important. Not just that they allow us to measure the output of the system, they also change the system. Whenever we measure a quantum system, the state gets changed, it gets affected by that observation. The third postulate describes how and what measurements are allowed. How measurements affect the system and what measurements are allowed. Our strategy to understand these would be to first understand simple kind of measurements which are called projective measurements. Those are the ones which we will use most often. Hence, it is important to understand these thoroughly. Then we will generalize these projective measurements to third postulate. That will tell us all possible kind of measurements. I would like to emphasize that most of the time in this course we'll be dealing with projective measurements. They are simpler to describe, so we should make sure that we understand what projective measurements are. Have you seen any measurement before? You might say no, but I think you have. Remember, we said that if our state is alpha 0 plus beta 1, then under some condition it gives us 0 with probability alpha square and 1 with probability beta square. This actually is a measurement in standard basis, 0 and 1. What happens to the state itself? At this point, just take this definition as some name, that we are measuring psi in the basis 0, 1. We know that we obtain 0, so the state changes to 0, we obtain the output 0 with probability alpha square. This is the complete description of the standard measurement. What happens is, if you're measuring psi alpha 0 plus beta 1 in the standard basis, you will obtain the output 0 and the state will change to get 0. This will happen with probability alpha square. You will obtain the state 1 and output 1 with probability beta square. Notice we described both how the state changed and the probability of the output. This gives us some intuition about how to describe projective measurements. In general, we would like to say that psi got projected into 0 when the output was 0, and the state psi got projected into 1 when output was 1. In other words, each output possibility corresponded to a projector, and if you look at the two projectors, this is the projector which projects on state 0, and if you look at the projector which projects on state 1, you will notice that P0, P1 is 0. In other words, these are projectors on orthogonal subspace. In this measurement, we noticed that for measurement, our state should get projected into some subspaces, and in our case, the subspaces were actually orthogonal to each other. This was the simple case, and we will define a general projective measurement just by taking these properties. Let's make it partially formal. If we have a state in C to the n, a measurement would contain projectors P1 to Pn. We need that these projectors are orthogonal. When I say projectors are orthogonal, it means that the subspaces which correspond to them are orthogonal, and second, they span the complete space. Again, I mean the subspaces corresponding to these projectors, they span the entire space. If we have a set of these projectors, then we would like to say that either our output would be P1 psi or P2 psi or Pn psi. This should be our output, and what should be the probability? The probability of getting into P1 or subspace of P1, that probability should be the norm square. You can convince yourself this is exactly what happens in the standard basis measurement. We had projectors. In the case of standard basis measurement, we had two projectors 0, 0 and 1, 1 of C square. Notice that the subspaces corresponding to P0, the subspace corresponding to P0 is span of 0, subspace corresponding to P1 is span of 1. These are orthogonal, and 0 and 1, they span C square. So conditions 1 and 2 are satisfied, and then when we say that alpha 0 plus beta 1 goes to 0, I am saying that the state is actually going to P1 psi divided by P1 psi. This division is necessary so that I get a unit vector. The final output should be at state itself, so I have to divide by this factor to make the entire thing a unit vector. If this had gone to alpha 0, this will not be a state. That's why we got this state, and the probability was alpha square, which was P1 psi whole square. P1 psi or P0 depending on whether it is projected into state 0 or state 1. Let's make this definition very, very formal. In the case of projective measurements, we describe a projective measurement by a Hermitian operator, which is sum of some projectors with a label. This is the label of Pi. I will show the importance, but important thing is summation Pi is equal to identity. Succinctly, this describes a measurement. How? We will notice that if we measure psi with m, the output would be mi. So that is why it is called the label for projector Pi. That's, we are just saying that, oh, the name of this is mi. It could be any number. That's not important. It's a label. But what I mean is that my space will be projected into Pi. So the state obtained will be this. Again, this is the normalization. This will be the state obtained. This will happen with probability Pi sigma whole square. From the previous description, the only difference is of these labels. You should not get confused about them. That is just so that we can write them as a Hermitian operator and it can describe some measurement value. So M is going to be a Hermitian matrix. MIs are going to be real. This is a spectral decomposition, and summation Pi equal to identity. Your question might be, here I have just given the condition summation Pi equal to identity. On the other hand, I wanted Pi to be orthogonal and they should have spanned the entire space. This was the condition before. It turns out, by the fact that Pi are projectors and Pi is equal to identity, actually implies this. And this is actually both ways. This you can take it as an exercise. Since these are equivalent, we capture this statement by this, and then we say that a measurement is defined by a Hermitian operator M, which is summation I equal to 1 to k mi Pi. Notice that given a Hermitian operator, by spectral decomposition, I get a list of projectors. My measurement is basically the measurement of these projectors. If someone tells you, oh, this is a Hermitian matrix H, this is the projector. What does it mean? This is a projective measurement. What does it mean? You just decompose it into eigenspaces, and this is same as measuring with P1 to Pk, labels of the output being lambda 1 to lambda k. And then, as specified above, I will obtain lambda I with this probability, and my state is going to be PSI as expected. You should definitely convince yourself that this is exactly the same as what happened in the standard basis. we have defined projective measurements now. You might be worried that why is the definition of measurement? Again, that will not be our concern. Why projective measurements or even the general measurements given by the third postulate? You might ask why projective measurements are the correct definition of measurements. We won't worry about this question. We will take postulates as written in stone. This question is better asked to a physicist. We will take this as our definition. We already know a simple measurement system, which was projective measurement. Basically, you take a partition, I should say, an orthogonal partition of your subspace, of your complete space, and then the measurement is that you are projecting your state into one of the subspaces. That's a simple measurement. It turns out that third postulate allows slightly more general measurements than that. We will study these in the next video, but most of the time this simple measurement, or what we call projective measurements, will be enough for our purposes.